So we go to the second speaker now. The second speaker is Charlie Wilson. Charlie, you are working here at IIASA and in the Tyndall Center for Climate Change Research in the UK. And the focus of your research is on technology and innovation systems. So this is obviously one of the important drivers of global change. What do you have to tell us?
Good afternoon. Technological change is central to economic growth, to societal development more generally, and is both cause and cure for the environmental impacts of growing populations and affluence. In this talk, I want to add a particular view of technology as both art and science, and how both these views help understand technology's role in shaping possible futures. Technology is most immediately thought of as hardware, devices, machines. Technology is also software, the know-how and the know-why embodied in people with skills or experience. Thinking of technology as skillful application underlines the importance of human capital set out by the previous speaker. It also points back to the origins of technology in the Greek words logos, reason or knowledge, and techne, art or craft. Technology appears sometimes literally as art. Hundertwasser's innovative cladding of Vienna's waste incinerator will be well known to the locals among you. More broadly, the artisanal characteristics of technology, knowledge of a craft, reminds us that like other forms of knowledge, technological knowledge can be generated and learnt, but also forgotten through obsolescence, depreciation, and turnover in human capital. As part of the global energy assessment, Arnulf Grubler at IIASA led a team of researchers on a comparative assessment of energy innovation historically. One aim was to distill out the essential ingredients of successful innovation. Sustained investments in the human capital, which underwrites technological knowledge, was one such ingredient. The 20 historical case studies we analysed, to be published soon in a new book, covered both relative innovation successes and failures. The Danish wind turbine industry is a good example of success. The US program to develop synthetic liquid fuels in the 1980s is an example of relative failure, as measured against its own goal of reducing US dependence on imported oil. A second essential ingredient of innovation success that we found in our comparative analysis, which again links to the importance of human capital, was that effectively functioning innovation systems involve a diverse range of actors and institutions, well beyond the usual suspects of R&D labs and commercial markets. The Danish case study is illustrated here not with a stirring image of turbines sweeping the land or seascape, but with a more prosaic picture of a blade being tested at a turbine test station. This was one of the public institutions involved in generating and exchanging knowledge during the successful development of a world-leading industry. So knowledge, human capital, actors and institutions are all integral elements of innovation systems. The hardware and software of technology are created and used in particular contexts, institutional, infrastructural, or organizational, giving rise to the term orgware, as coined originally by IIASA scholars. We encapsulated these various characteristics of innovation in a framework comprising innovation stages, from research and development all the way through to commercial deployment, innovation drivers, both technology push and market pull, and innovation processes, which contextualize and link these stages and drivers. These innovation processes are many and varied, relating to knowledge and its generation and use, to actors and institutions with their risk preferences and expectations, to the mobilization of resources, both financial capital and human capital, and to the adoption and use of the technologies themselves. This innovation systems framework not only allowed us clearer insights into why some innovations had succeeded historically where others had failed, it also gave us a comprehensive and transparent way to analyze current innovation activities. We looked first at the respective contributions to climate change mitigation of energy supply technologies like power plants and refineries, and efficient end-use technologies like buildings, vehicles, and appliances. Global and national modelling studies show changes in energy end-use may contribute over half the required reductions in greenhouse gas emissions, a point we also heard on this morning. Efficient end-use technologies also outperform their energy supply counterparts in terms of their impact on economic productivity, their broader environmental, social and energy security benefits, and their potential for learning to improve cost and performance, and hence their market appeal. So we then asked, how well aligned are current innovation efforts being directed by public policies, public institutions and public resources with these clear potentials for efficient end-use technologies? We sampled a wide range of data describing all the elements of the innovation systems framework I showed you previously, and a few of these are shown here. We looked at knowledge, including modelling and research. We looked at institutions, including technology roadmaps, which enshrine shared expectations, and also international technology collaborations, both bilateral and multilateral. We also looked at resources, including financial investments in research and development in both developed OECD countries and in the major developing or BRICS countries. And as can be seen, this systemic analysis reveals a striking misalignment between innovation outcomes and needs, which emphasize efficient end-use technologies, and the efforts and activities being currently directed to meet those needs, which emphasize energy supply technologies. This carries a provocative implication for public policy. Current innovation efforts for climate protection, whether relating to knowledge, institutions, or resources, need rebalancing in favor of efficient buildings, vehicles, appliances, and other end-use technologies. This is important because current innovation efforts circumscribe the future possibility space for technological change. Modelling and scenario analysis work at IIASA as part of the Global Energy Assessment has found that efforts to improve end-use efficiency dramatically increase the options available for the energy supply. The Gaia efficiency pathways, showing the potential for energy savings, represented by the grey block on the top, allow flexibility in which and how much energy resources are used, represented in the coloured blocks beneath. The Gaia supply pathways, which lack these large and sustained energy savings, have no such flexibility. In other words, innovations in energy end use ensure us against potential innovation failure in any of the low-carbon energy supply technologies. Two of the research frontiers for improving our analysis of energy end use relate to how we understand, represent and model people, with all their wonderful irregularities, or more soberly, irrationalities. These are particularly relevant given what we call the granularity of end-use technologies. They're small scale, relatively low cost, large in number, dispersed and highly heterogeneous. Understanding the adoption and use of these granular technologies poses a major challenge. Work just beginning at IIASA, led by Keivan Riahi and the Energy team, aims to develop the next generation of models by progressing on both these fronts, and in so doing, help resolve more clearly the possible futures described by technological change. In conclusion, I've argued for a view of technology as artisanal, skillful application, both learned but also forgotten without sustaining investments in human capital. Technology is hardware, software and orgware, which can be analysed and directed, or misdirected, as suggested by our analysis of current innovation systems for climate protection. And technology as the possible, particularly end-use technologies, which will play a pivotal role in the unfolding future of a warming planet. This is the central theme of English writer Ian McEwan's novel Solar, another treatment of technology through the lens of art. The book is woven around a breakthrough solar technology, heralded as a silver bullet solution for climate change. But its protagonist, the solar power entrepreneur, has a personal life of gluttony and insatiable appetite. This serves as a darkly comic allegory for humanity's own conflicted capacity to rein in the consumption enabled by technology, when all the signs are warning to do just that. The book thus sheds an awkward light on the codependencies between technology and people. Thank you.